Hi everyone, welcome. My name is Sumit Patidar, and I am presenting our work with Adrian Sealer and Oliver Brock on in-hand cube reconfiguration simplified. Recently, several manipulation systems have been designed to solve cube reconfiguration tasks, and it has become the benchmark problem in robot manipulation. The objective here is to reorient a cube within a robot hand to any arbitrary rotation. And it seems a challenging problem due to high dimensional action and state space, contact dynamics, slippage, and many more. It is great that people have solved it in different ways, mainly either by throwing high dimensional data to a reinforcement learning agents or using motion primitives. This paper is trying to explore the question, what is the right way to tackle in-hand cube manipulation? To investigate this, we try to make control and planning as simple as possible and see if things work out. So let's dive straight into a spelling demo. Here we have a soft robotic hand, namely the RBO-N3, attached to the Francapanda arm. There are three different objects, two cubes and one cuboid, lying on the table surrounded by a wall. What is going to happen next is the robot will pick the objects, reconfigure them, and place them back on the table one by one. So let's get started with the Rubik's Cube. If you notice that the cube is first dragged into the open space and then grasped. This is to avoid collision with the wall, and the dragging motion is open loop. This is made possible by using a general purpose soft dexterous hand. Now what happens next is even more interesting. As you can see, the hand is configured in different configurations, and gravity is used as the only actuation source by employing wrist motions. And if you carefully observe, you will find that the object is not firmly grasped during manipulation. It is moved inside the cage formed by the hand. And this is all execution of open loop primitives. These primitives act as funnels and they are sequenced using strips planning. There is no feedback or sensing involved. And what makes these primitives robust is the compliance and the constraints offered by the soft hand. The keyword manipulation is an interesting one because we execute the same primitives with identical actuations for all objects, unlike deep reinforcement learning where we have to learn a new policy for a new object. And looks like it handled it pretty well and is having a fun time. Why is this so impressive? The answer is simplicity. Let's analyze the complexity of different approaches. Most of the in-hand cube manipulation methods rely on deep reinforcement learning to learn policies for dexterous manipulation. And this requires a large amount of data, computation time, and sophisticated sensing to learn millions of parameters. This all adds to the complexity of the system. However, there also exist simpler systems relying on motion primitives, which either use complex modeling with feedback or just open loop control but requiring large number of keyframes. Our approach is even simpler because in addition to open loop control without any modeling, we employ wrist motions. In all other works, the object is firmly grasped, which is difficult to control because of intrinsic dexterity. None of them leverage the full potential of wrist movements to generate robust dexterous behavior, which can actually reduce the strain on intrinsic dexterity. With our findings, we come to the conclusion that applying deep learning to in-hand cube reconfiguration is not required. Instead, understanding the problem, choosing appropriate hardware in conjunction with the control approach for a given task leads to task simplification. And lastly, the combination of learning with the insights we gained has a huge potential to build more robust manipulation systems. Here are some of the references, and we thank our sponsors for all the love, support, and funding. Thank you for your attention. I hope you enjoy reading our paper. Goodbye.